Hi Matrix. Today we're going to look at dihybrid crosses. If you are following in your textbook, we are on page 65. And so just to recap what we've already done in genetic crosses, which are monohybrid crosses. Mono meaning one is when we cross one characteristic. Now in dihybrid crosses, we are going to cross two different characteristics. In other words, we are no longer just going to cross color. We are going to do color and perhaps texture at the same time. So when we look at the word dihybrid, di is obviously referring to two, and that means we are going to then use two different sets of alleles to do these crosses. Now, that then means that we can use many different sets of alleles to do these crosses. We could use height, we could use color, we could even, which does make it a little bit more complicated, just keeping track of all the letters, but we could even use sex-linked disorders. And you can also find dihybrid crosses that contain blood groups. Now, what's linked to dihybrid crosses and the fact that you use two sets of alleles is the Mendel's law of independent assortment. And effectively what it is that different allele pairs separate independently of each other in the formation of gametes. So what does that mean? That means that if you have two characteristics like height and color, they are independent of one another and they will separate from each other in the formation of gametes. Now, for now, that's a little bit abstract because we can't see it actually happening, but when we do the Punnett square in the next slide, you'll see what I mean by separating the alleles. Now, to keep this example simple, for now I'm just going to use color and height as our explanation. Now, with color and height and dihybrid crosses, you are still going to use the lettering that we are familiar with. In other words, you are still going to use big and small letters, or uppercase and lowercase letters. Except this time, you are not going to write down just one set of letters, for example, a big and a small letter. Instead, rather, you are going to need to include two sets of alleles. And that's what makes it a dihybrid. You have a set of alleles for the height, and you have a set of alleles for the color. So what are we going to do now to illustrate this? So, if, for example, I let the capital letter stand for tall, and I'm going to use a small t for short. For color, I'm going to use the capital R for red and a small r for yellow. This set of lettering is what we're going to use when we're going to do our P1 cross, so our first parental cross. And so when we do a dihybrid, it's always important to remember that it must have two allele sets. In other words, you must have two different letters appearing. So you must have T and R. So what does that look like? Well, we're going to start off with the P1 generation, and it's going to be a purebred generation in that our parents are going to have a set of alleles that have a homozygous appearance, just like that. And so if we were to take our parental alleles, like the ones I've put below here, we are going to have a tall red individual with a short yellow individual. And so if we were to put that into our genetic cross, it would look something like this. So we have our first parent, who is tall and red, multiplied with our short and yellow parent. Now, for simplicity, I am leaving out some pieces of the genetic cross so that we can move through this easier. Now, the difficulty in dihybrid crosses is creating the gametes, and this is where most of the mistakes come in most often. And that's because there is more than one set of letters that you need to be aware of. And so, however you would like to keep track of how many times you've used each letter is up to you, but I just rule a line under each letter to make sure I've used each one at least, to a maximum of twice. So let's make our gametes. So just like before, you are going to work with one group at a time, or one parent at a time. So let's make my first 4 gametes. So I'm going to take the first letter T and the first capital R, and I'm going to make my first gamete. And I will do it again. I'm allowed to use this capital T once more, and I'm going to use a different R this time, and I've now made my second gamete. And you will do it again for the second letter T and the first letter R. And as you can see the pattern, you should have 4 alleles that are all the same. Capital T, capital R. And that means that at the end of this, you would have used each of those alleles for a maximum of twice. Now we need to do the same for the other parent. So we're going to take small letter T, small letter R, and put that into a gamete. And we'll do it again with the next little t and little r. And once more. And you should have now, if you've done this correctly, you would have used all of your letters twice, and you would have now 8 alleles. Now, these alleles need to be transferred into your Punnett square. So I've put the Punnett square on the next page, but of course when you're doing this you want to have it as best as possible all on the same page. Alright, so if we were to copy these 8 sets of gametes into our Punnett square, it would look something like this. Keeping in mind yet again that we want to keep our gametes and their alleles in the correct columns and the rows. We don't want to separate them and mix one parent's alleles with the other parent's alleles. And so what we can start doing now is we are going to fill out our Punnett square like we normally would. And so I'm going to start filling it out from the top right hand corner. Now you will start to notice that there is obviously a pattern in this particular cross, in that you will see that all of our individuals are going to come out the same. And we know this to be true because whenever you cross a homozygous dominant individual with a homozygous recessive individual, all of your offspring are going to appear as heterozygous. And so for simplicity, and also to keep this video short as possible, we are going to assume that the rest of this Punnett square will have exactly the same lettering in all the empty spaces that I've left here, because all the lettering is the same. Right, so let's now do our pheno and genotype. So for this example, in our genotype, we have 100% capital T, capital R, little r. And in terms of our phenotype is going to be, I just need to erase this. Our phenotype is going to be 100% tall and red. So for now, the cross is fairly straightforward because all the individuals are identical to one another. They're all going to come out tall and red because tall is the dominant allele here and red is the dominant allele, and each one of the offspring contains at least one capital T and one capital R. Now let's go into what makes dihybrids slightly more complex. What happens if you were to take two of these individuals? So let's say we took this individual and this individual here, and we interbred them with one another. And that brings us to the F2 generation. And so what we're going to do is we are going to now cross and interbreed two of these individuals with one another. And so that means they are heterozygous. So they're going to have a big letter and a small letter for the letter T, and a big letter and a small letter for the color. And we are going to multiply it by the same for the other individual. And just as a reminder, that means that this individual is tall and red, and this individual is also tall and red. Please keep writing this out correctly. I'm only shorthanding this for the lesson. So now we need to make our gametes. And yet again, we need to keep track of which alleles we have used and which we haven't. And this is often where most mistakes are made. Please keep track of them, especially in the P2 cross. So let's begin. And remember, we do one set of alleles at a time, meaning we do one parent at a time. So you're going to take one letter T and the other letter R, and I'm going to put that in a gamete. Capital T with the small r. I've used the capital T twice, so I can't use it again. Now I'm going to use the small t and the capital R. A common question is, which letter do we write first? Do we always write the capital letters first? You don't always have to write the capital letters first. Effectively just use the ordering that they've given you in your test or in your exam. Let's use the last T with the small r. So now we've done our first 4 alleles for our first parent, and if we were to do it for the second parent, then we would end with the same set of alleles because they have the same set of genes. Alright, so now I have quickly included the second set of gametes. So yet again, you should have, if you've done it correctly, 8 gametes. And each of your gametes may only have one allele of each characteristic. And that's how independent assortment works. You can never have 2 letter R's or 2 letter T's in your gametes. You can only have one of each, 1 T and 1 R. If you have more than that, it then means that you have made a mistake. So now let's have a look at what the Punnett square will look like when you put all your lettering into it. Alright, so now what I'm going to do is I'm going to copy these gametes into their Punnett square, which I've just done here, keeping in mind that your Punnett square needs to be big enough to include everything. So now let's cross our gametes with one another and let's see the different combinations that we get. So I urge you to do this fairly slowly in the beginning, especially when you're just starting out, because often this is where the majority of mistakes arise, is you don't copy your lettering correctly and you end up making a silly mistake. Now all I'm doing is I'm crossing my column with my row each time. So I'm starting on the top and I'm going big letter T, big R, small r, big letter T, small r, big T, small t, big R, little r, big T, small t, little r, little r. Now I'm going to fill out the rest of the Punnett square to save time, and then I'm going to show you how we write our pheno and genotypes. Alright, now that I've filled out my whole Punnett square with the remaining combinations, I'm going to write the phenotype. And all I've done here is I've written phenotype, and I have listed the possible combinations. So tall and red, tall and yellow, short and red, and short and yellow. And so because we're doing all the phenotypes, we need to select all the allele combinations that represent these phenotypic outcomes. So to be tall and red, you need at least one capital T and one capital R. And so what I like to do is I'm going to pick a color, and I'm just going to highlight all of the tall and red individuals. So they need to have at least one capital R and one capital T. So this individual here, this is a capital T and a capital R, capital T, capital R, capital T, R. There's another one, and there's one. Okay, I think that is all of them. Right, so now that I've highlighted all the ones that are tall and yellow, I can write that as a fraction. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 out of the 16 that are tall and red. Now I can use a different color to look out for our tall and yellow. Tall and yellow is going to be a capital T but two small r's. So I've got a tall yellow individual here, tall and yellow, tall, yellow, and that's it. So now I have 3 out of 16 that are tall and yellow. And I'm going to do the same for short and red, and I suggest you do this with highlighters as well, or even a little dot or star, and put them all together so that you know who belongs with who. Short and red means I'm going to need 2 small t's and at least 1 capital R. And so I've got 2 small t's here with a capital R, 2 small here with a capital R, and 2 small here with a capital R, which means I now have 3 out of 16 that are short and red. And that then leaves me with the very last option, which is short and yellow, and we only have 1 of those, and so that means we are going to have 1 out of 16. Now this makes effectively a golden ratio, if that's what you want to call it, and it is an inheritance pattern which is exclusively linked to dihybrid crosses, and it can be used as a reason for crossing heterozygous individuals and explaining how patterns arise. And so to do that, all you need to do is you are going to have to write the ratio, which in this instance is 9 is to 3 is to 3 is to 1. And this ratio is closely linked to dihybrid crosses. You can find a little paragraph explanation on page 67 as to why we need to determine these ratios. As for dihybrid crosses, this is one of the simplest ones that we can do. Like I said, we can also do sex-linked and blood grouping, which means you can do perhaps hemophilia and blood groups at the same time. It does mean you need to be a little bit more careful so you don't confuse your lettering and you don't lose your place while you're doing your crosses. But effectively, as if you do it slowly and you make sure that you write out your gametes correctly, there is no way that you could make a mistake. If you have any more queries on your dihybrids, please reach out to your respective teachers and they can clear up any other things that you need to know. Otherwise, make sure you complete the activities that we've submitted onto Google Classroom. The good news about dihybrid crosses, which I've sort of saved the best for last, is you will never be asked to do a complete dihybrid cross in an exam, and it will never be asked in its entirety at the end of the year. Instead, at the end of the year, you will be asked to fill in missing pieces of information. So you could be asked to fill in a Punnett square that is missing blocks. So there's like an empty block and you have to fill it in, or you have to give the ratio, or you have to list what the parent genotypes were based on what the offspring genotypes were. A good example of what this would look like is the activity that I have uploaded onto Google Classroom, which is based on dihybrids. It's a great way to see how it's been asked, but if you need any more clarity on that, please reach out to your respective teachers.